what we are really looking at since last lecture is suppose A is a matrix of the size m by n, say for example. B is a vector which is in Rn. Then the question that is being asked is, does there exist an X? Does there exist an X in Rn such that Ax is equal to B? Okay. So that is the question that we are asking. Does there exist an X in Rn such that Ax is equal to B? So this X is called as solution of this system of linear equations, right? And last time we geometrically tried to understand what it really means. So when you look at this Ax, what does this Ax really mean? Ax is X linear combination of columns of A, right? So what is X linear combination? X linear combination is basically if A1, A2, An are columns of A, then X1, X2, Xn are components of this vector X, then A1, X1 plus A2, X2 plus A3, X3, right? So X linear combination will basically mean A1, X1 plus A2. Okay, so maybe I used a symbol which was small case letter, A1, X1 plus An, Xn, right? Where AIs are columns, A1, 2, An, the columns of A, and X is this particular vector X1, X2 up to Xn, right? So what we really look at when we see Ax is the column linear combination. So if B belongs to column space of A, if B belongs to column space of A, which is nothing but span of these vectors A1, A2 up to An, then what did we say? We say that there exists an X. That means that you can write down B as a linear combination of columns of A, right? So this was the condition that we saw last time. We derived this condition. And furthermore, what did we learn? Furthermore, what did we learn was that if these columns of A1, A2, An are linearly independent, so columns of A1, A2, An linearly independent really means that they span the entire column space, right? So it is not necessary every time that they will be bases. They will span the column space. Sometimes the columns may be linearly dependent for the matrix A. But if they are linearly independent columns, then what it really means is that they span the column space of A, not only that they are bases, right? So if columns of A form basis for column space of A, then there exists a unique X, right? Unique linear combination, because you know that every vector can be written as a unique linear combination. So what are the two conditions for the uniqueness? The first condition is that the B vector should be in the column space of A to start with. And if it is column space of A, and if columns of A form basis, then you know that you will be able to express B as a unique linear combination of columns of A. So these are the two conditions. So the first one is existence condition, and the second one is uniqueness condition, right? So these are the two conditions. So you might have seen these conditions in different notation, different forms. That's fine, but this is the way. This is the geometrical way that we will look at, and we will focus our attention. Okay. So we defined, I think, what is the rank also. So I think in the last class we defined rank of A to be the dimension of this column span, column space, whatever you want to call it. Okay, right? So this is something that is important. So rank of A. So now you see, if rank of A and augmented rank AB, you say that is same, then there exists a solution, and so on and so forth. You have those conditions, right? So that really is saying that these are the columns. And uniqueness in the uniqueness of solution is guaranteed by the basis. So this is what we were talking last time. Any doubt about this?
Hello, sir.
Huh? Yes.
Yeah, like there exists unique X when the columns of A form basis for R for Rm, right?
No, columns of base, no, form basis of column space of A. And if B is in the column space of A, you don't need it to be in Rn, Rn.
So, but anyways, the columns will form basis for column space, right? Sir?
Yeah.
But for existing of uniqueness, they should have to form the basis for R power M, right? Rm.
Why? Why?
Uh,
They need not, right?
Okay, okay, okay.
Yeah, so don't think of square systems all the time. We are not talking of square systems. In fact, in this course, we will not talk of square systems much. The type of linear equations that we will be interested in will be either system of equations which are overdetermined or underdetermined. And some places will talk of system of linear equations which are square. But in AIML type of applications where you want to work, the system of equations that typically you get in least squares problem, you have more number of data points than the attributes, right? So that really means that you have more number of rows than columns. And then you want to solve the system of equations, you will always end up with a rectangular system of equations. Or in the problems like basis pursuit problem or compressive sensing problem that you think of, the system of equations will always be wide. You will have less number of equations than unknowns, right? So these are the type of places where we are interested in computing solution and understanding the solution. So don't think of only square system of equations only. Okay, now we have to think beyond that. Is that okay?
Yes, sir. Thank
Okay. So simple thing that we will now look at is that once we understand this theory of existence of solution, uniqueness of solution from the linear algebra point of view, the natural question arises: all these things are fine, but if I really get a system of linear equations, how am I going to check whether B belongs to the column space of A to determine if the solution exists or not? How am I going to compute that linear combination, unique linear combination of columns of A such that Ax is equal to B? So this understanding is one thing, but the computation is other thing. We want to be able to compute also, right? So there are few tools, there are few techniques which can be employed to solve the system of linear equations. Okay, so now I will list three questions, three things that we will really do with system of linear equations. Okay, so system of linear equations. First thing is understanding, okay, what it really means, understanding the existence, uniqueness of solution and so on and so forth. Okay. So this is something that we have already done. Okay, then we want to do the computation part. Okay, so computation of solution, that is second aspect. Computation of solution. And the third thing that we want to do with this is sensitivity analysis. Okay, so what are these things? So this we understand. Computation we will see now. Okay, for that there are certain tools that we need to develop. We will develop those tools. That's fine. And the third part is sensitivity analysis. So sensitivity analysis again is something that is very important and has very far-fetching repercussions in practical applications. Okay, so suppose you have Ax is equal to B. Okay, suppose you have Ax is equal to B. You learn the computations, you find out the solution X, you compute the solution X. Okay, so X is the solution. But in real life applications, what is really happening? In real life applications, whatever reason may be, you are not able to express B and A exactly. Okay, so there is some A and there is some B, but because of practical constraints, the constraint starts from storing the numbers in a computer. Like in a computer, you cannot even store number 1 by 3, right? There is a problem. you can never store number 1 by 3 accurately. So if on the right hand side B it is 1 by 3, then you will never be able to store 1 by 3. 0.33333, you have to do it in infinitely many times to get 1 by 3. But in real life you cannot have those many bits in a computer, right? So you will always approximate. So there are errors that are already there in storing real numbers in a computer, right? So the problem starts from there. Then there are problems like many a times the way A and B you will get here, they will be collected after doing experimentation or after collecting the data, so to speak, in the language of AIML, right? So that data might be, you know, you are measuring heights of people and putting those heights in column B. Now, when you measure the height, there is always a problem, right? Exact height you cannot measure, come what may. You are doing it with a measuring tape, the least count of measuring tape, at least that much error will be there. If you are measuring weights and putting in there, you know the least count of weight meter, then there is a problem with that. You are measuring currents, you are measuring voltages, you are putting those values there in A and B, right? You are measuring blood sugar level and putting it there. Any application that you think of, whatever measurements that you take, they are prone to error, right? So the observations that you put in here in B or in A, they're prone to error. So you will never have A and B stored exactly. So what happens is you will always have, instead of A, some perturbed version of A, and instead of B, some perturbed version of B. So in reality, the system of equations that you will be solving is this. You really wanted to solve Ax is equal to B, but in reality, because of all these several reasons that I mentioned, you will be solving this second system of equations, not the first one. Now the natural question arises, okay, so the errors that occur in A and B, you see these errors that occur in A and B, they're not much, okay, they are insignificant, so to speak. Insignificant meaning not much, okay, they're comparable to A, they're very small. Okay, that is what these errors are in A and B. But then, does that guarantee that X and X tilde also be close to each other? That is the question that we are asking. Does that mean X and X tilde will be really close to each other? So if that is guaranteed, then you do not really worry too much, right? Because you are solving an approximate problem, and the solution to the approximate problem, which is 2 and X tilde, is basically close to 1 and X. Okay, so that is not a problem. But is this guaranteed, given that A is perturbed only ever so slightly and B is perturbed only ever so slightly, X tilde will be close to X? Is it guaranteed always? What do you think?
Not always, sir.
Not always. Why do you think?
Because it's a breakdown.
So the addition of small delta A could result in change of sign as well, which could ultimately result in change in the determinant values, and hence it can have some impact.
So determinant is something that we will not even speak of in this course. Okay. So what we want to do here, determinant will absolutely of no help. It's okay, but that's okay. That's fine. What you are saying, okay.
One of
So
the
that
ways
small
we are
change might lead to
multiplying X by A. So the combined product of delta A and X tilde might be large. So we cannot just assume that X and X tilde are close, because it is getting multiplied by something else, A, delta A into X tilde. So we cannot assume.
Correct. So there is a multiplication by delta I happening, and how that multiplication of delta I really affects is what is going to determine if X tilde and X are close to each other or not. Okay, so this is something that we want to investigate. So this comes under the topic name, which is called as sensitivity analysis. So given a system of linear equation, the first task is done. Second task is something that we'll focus on right now, and the third task is doing sensitivity analysis. So here we are talking of all the terms like near, small perturbations. So this near, small, all these things need to be quantified. So you must have seen in one of the video lectures that I shared, this quantification is done through something which is called as norm, right? So you would have learned what is vector norm in those lectures. So first tool to look at this is something which is called as matrix norms. So we will first define what the matrix norms are, and once we understand what matrix norms are, using those matrix norms, we will do this sensitivity analysis, and we'll do this sensitivity analysis to understand how this x tilde changes. Is this x tilde close enough to x, and so on and so forth. Okay, so this is something that is extremely important, because many of you already know that this system of linear equations has direct relationship with regression problem, right? And in the regression problems, this x is actually the parameters that you estimate. And now what is question that we are asking from the context of AI ML application? The question that we are asking here is that the data that you have, the measurements A and B, right? So this is the data that you have. This is the data that you get. So we all assume that this data is corrupted by noise. Every time we assume that this data is corrupted by noise. So you always have access to A plus delta A, B plus delta B. So if this x tilde, the solution of nearby problem or the solution of approximate problem, if it is not close to x, that means that the parameters for the regression problem that we will estimate, which will be x tilde, those parameters will be too far away from the true value of the parameter x. That's what we are really saying. And does that help us? Probably not, right? Because the parameter estimation problem in regression is something that is of importance to you, because these are the model coefficients, model parameters that you are learning, so to speak, from the data. And you are saying that if the data is perturbed ever so slightly, these parameter values can drastically change. That is something that is not desirable for us, right? That is the stability of, so to speak, or the variability in the parameter estimate we are saying is really too high. We will not like such a situation to arise, right? Typically. So this is something very important. This is a very basic problem in regression, right? So we will understand this problem through this sensitivity analysis. And here, of course, we will learn all these important decompositions. So while we are going to do the computation of solution, we are going to learn various techniques like LU decomposition, QR decomposition. And when we are doing sensitivity analysis, we are going to learn something which is called as SVD. So the singular value decomposition actually is very important. You might have heard something like condition number. So that condition number really comes into the picture with this SVD. And that condition number has a very beautiful geometrical interpretation that we can learn through matrix norms, their connection with these condition numbers, and how SVD comes to the picture, and how we can actually derive beautiful results about, how far x tilde will be, what all it depends on, and things like that, right? So this is something that we want to do, and this is something that we want to do typically for two types of system of equations, one square and other tall. Okay, so these are the two types of system of equations. We'll focus mainly while doing this, and then after this we'll focus on to the system of equations which are wide, right? So that is something that we want to do. So in next few classes, maybe 2 weeks or so, this is the plan. This is what we are going to do. So I will be jumping back and forth between various concepts in linear algebra, but something that you should be always aware of is that this is the flow. Okay, this is what we are going to do in next 2 weeks. So the first thing is done, understanding existence uniqueness of solution. The second thing is computation. So in order to compute, I am going to set up various machinery. So I will be doing LU decomposition, QR decomposition, all those different types of things. There I'll be using concepts. So I'll be going back and forth. Okay, something happened. I don't know. So I'll be going back and forth in these equations, and there will be a lot of jumping around. That's why I just wanted to put this forward, right? This is what. Oh God, I don't know. So this is what we have as our objective, right? So these are the three important things that you should be able to understand. So this is the learning objective for next 2 weeks. These three concepts we should completely understand. So this is what we are going to do. So let us go into this computation of solutions. Okay, so the part that we will focus now on is computation of solutions. So suppose you have a simple equation, okay, scalar equation. So if you have a scalar equation, alpha, because x is equal to b, is a into x is equal to b, where a is a scalar, b is a scalar. Can you find out x which satisfies this ax is equal to b? This is a particular case when m is equal to n is equal to 1, right? The obvious thing for you to do is you write a 1 by ab, or you write x is equal to a inverse b. But can you write a inverse b always? You will say no, you cannot write always, provided that a is not equal to 0. You can write down x is equal to a inverse b. So this is so natural, so easy for us, right? This has been something that we have been seeing. But the question that we want to ask now is that suppose you had a system of equations ax is equal to b, where a is a matrix of size m by n and b is a vector of size rm. Then what we are really saying is that can we generalize this process? So this process that we had here, can we generalize it to obtain this particular solution, right? Computing solution of x. So natural thing to understand here is that what is the inverse of this real number, right? So if I can associate a concept of inverse with respect to matrix, then possibly I can do something similar and I can obtain the solution x, right? So that's the reason I will first start talking about the inverses of the matrix, right? So I will first understand what is inverse of a matrix. Once I understand what is inverse of a matrix, then I can start generalizing this approach in the scalar case to the vector case or the matrix case. So that's what I will do. Okay. So the first thing that I want to define is a left inverse of a matrix. Okay. So left inverse of a matrix. Left inverse of a matrix. So a matrix X, so I'll write down the definition, a matrix X that satisfies XA is equal to identity, okay, is called left inverse. And the matrix A is called left invertible if the left inverse exists, okay. So suppose A is a matrix which is of the size m by n, then what do you think should be the size of X?
N cross 1.
N cross M.
N cross n. Left matrix will have size n cross n. Okay, we'll see why. But let us quickly see some examples. Okay, so the examples will give you some idea. So suppose the first trivial example is A is the scalar A, the one that we were speaking of here in the first equation. Then what do you think is left inverse of A? Simply 1 by A, which is sometimes will denote as A inverse, right? So what is the identity here? Identity here is matrix 1, right? So I can write this in matrix form like this, or I will not use the braces, the matrix braces, right? The second example is something which is very interesting. So suppose this matrix A is actually a vector Rn by 1. It's a vector Rn by 1 and it's a non-zero vector, for example. Okay, so there is at least one entry there which is not equal to 0. Can you tell me a left inverse for this particular matrix? Can you tell me a left inverse? So you have to have a matrix X. That matrix X will multiply A and you will get identity. So the identity will be the constant one, right? So can you guess a vector X which will satisfy this?
Sir, the inverse of each element into 1 by n. And
Inverse
it will
of
be a vector.
Inverse of each
Like
element
if
into 1 by n. So suppose A is 1, 2, 3. Then what you are saying is X is equal to 1 half 1/3. Is that what you are saying?
sir, and then each multiplied, like the whole vector multiplied by 1 by 3.
Whole vector multiplied by 1 by 3. So if you multiply this, then do you get Xa is equal to 1? 1 plus 1
Yes,
plus
sir.
1, 1 by 3, 1. You get this. If something is 0 here, Kshitij, if something is 0 here, what will happen?
Sir, it won't give us 1.
No,
Means
then what will
I
you
will
do?
have to
Sir, there
How will you
is
replace
an
the
modify?
1 by 3 by 1. Like I will
1 by
do it 1 upon n minus 1.
So do it
Sir,
1
it's
by. So
One
do
all
it.
non-zero,
and
one
all zeros.
non-zero element should be inverted and remaining all should be zero.
Sir, 1 by
No.
AJ into EJ.
1 by
1 by AJ into EJ.
into EJ.
Yes.
But provided that AJ is not equal to 0, that's what you are saying.
Yes.
And do you take EJ or what do you take?
EJ
is a
transpose.
EJ transpose. Okay, so that is another option. So clearly this is different than this that Kshitij has suggested. So what Kshitij said here can definitely be modified provided that if there are 0 entries, suppose there are k 0 entries, then in the left inverse also you put zeros in the appropriate places, and 1 upon n minus k is what you do. That's what Kshitij suggested. You can easily do that. Definitely this left inverse is different than the left inverse that Sumant suggested. Sumant, is that you? You said that?
Yes, sir.
Okay, so you suggested this. So this left inverse is definitely different than the left inverse that was suggested. So it looks like left inverse may not be unique. Left inverse may not be unique, right? So left inverse is not. So what vectors A you will not so kind of disqualify from the case that you cannot compute inverse. So for which vectors you cannot compute left inverse?
Zero vector.
Only the 0 vector. Correct. Only the 0 vector. For all other vectors, all the non-zero vectors, you can always compute a left inverse. So this being a very nice formula, at least one entry of A will be non-zero. So you pick that entry, the first entry, non-zero entry that you encounter, and you write down 1 upon AJ into EJ transpose. Right? One more example will be. So suppose matrix A belonging to Rm cross n is such that A is equal to A1, A2 up to An. There are n columns. Each column is of size Rm, right? So m vector, right? Aj belong to Rm. J is equal to 1, 2 up to n, right? So this is what you have. And the columns of A are orthonormal. So do you understand what is the meaning of columns of A are orthonormal? You take inner product of columns among themselves. So AI transpose AJ, or you will write this as AI AJ, inner product, whichever notation you want, will be equal to delta IJ. So I and j is equal to 1 to up to n. What is delta ij? Delta ij will be equal to that Kronecker delta, right? So delta ij is equal to 1 if I is equal to j is equal to 0 if I is not equal to j, right? So this is the Kronecker delta function that you have. So if the columns of A, then do you think this matrix A will have left inverse? What will be the left inverse here?
A transpose.
A transpose, correct. A transpose will be the left inverse because when you multiply A transpose to A, you will get identity. What is the size of identity matrix that you will get here?
N cross
N cross
N.
N.
cross n.
N cross N. So how does the matrix A really look like? Is it wide, square, tall? How does the matrix A look like?
Sir, it should be tall.
N into 1.
Huh? It should be tall. Why it cannot be wide?
Tall. N into 1.
Sir, independence dimension inequality.
Correct. So that tells you that you can have at most uh, m number of orthogonal vectors or basis vectors or linearly independent vectors, right? So here n has to be less than or equal to m. So it can be a square matrix or it can be a tall matrix, but this cannot be a wide matrix given that columns are orthonormal, right? So that is something that is really, really important. One more example I just.
Sir, is that a property of orthonormal
Huh?
matrix? Is that a property of orthonormal matrix?
No, it's not a property. It is a consequence of that dimension property that Kshitij was mentioning. It is proved in lecture 6 that I have shared. It follows. It's a consequence. Okay, it's not something that we assume. It is a consequence. Okay. You cannot have more linearly independent vectors than the dimension of the space, right? So the dimension of the space here is m. So you cannot have more than m linearly independent vectors. Now I'm saying the vectors are orthonormal. So if the vectors are orthonormal, then it means that the vectors are independent also. So if I'm giving you a collection of independent vectors, orthonormal to be specific, in the space Rm, then that collection size should be less than or equal to m. You cannot have more than m linearly independent vectors in R. Is that okay? That's the reason why your n has to be less than or equal to m.
Yes, I got it.
Yeah. One more example I just want to take. So this matrix, is it left invertible? Suppose I call this matrix A and I give you B to be equal to 1 by 9 into this matrix. Is the B left inverse of A? Can you quickly check on that?
Yes, sir, it is.
Can you give me one more matrix which will be left inverse of A, not equal to B?
So multiply the b inside by 2 and divide by 1 by 18 instead of 1 by 9.
But that is the same matrix. No?
So you need different one.
Yeah.
The transpose of A.
Huh?
Is can C be transpose or A, or should we give it some other example?
Will transpose of A in this case be the left inverse? You multiply by transpose of A2 and check it is left inverse or not.
So we can just put 1 by 8 there and there.
What is it? Can you say again?
Instead of 16, we can write 15, and instead of minus 15, we can write minus 12. And outside, what we can write 1 by 8, and we can just play around.
But that is the same matrix, no?
No. Oh, the matrix is 1 by 8, minus 11, minus 10, 15. 7, 8, minus 12.
What is it? Minus 11.
Minus
10.
15.
15.
Yes.
And
7, 8. minus 12. And outside 1 by 8.
1 by
8.
So do you get identity?
Yes, I think.
I don't think so.
Sir, we'll get just reduced it by 1 and then.
What? Just?
Sir, we'll get identity matrix.
You'll get identity in this particular case. I am not doing matrix multiplication. Will you get or not? I'll take your
Yes,
word
sir. Yes.
So no, sir, no.
Sir, a simple matrix can be calculated. 1 1 0 1 1 minus 1.
1 1 0
1 1 minus 1.
So this is your C. Then what happens?
If I multiply,
you get identity. Okay. So are you convinced that there are more than one left inverse that may exist? So immediately when we go to the vectors case, it looks like here in case of real numbers, there was something unique about the inverse of this number, right? But here in this case, it looks like there may exist more than one inverse. Okay, I'm not sure about this. Okay, you please just check and find out whether this is indeed a left inverse or not. There are more than one left inverse, that is possible. Okay, so these are several examples. So let us investigate what is happening with this left inverse. Okay, so left inverse and some property. Okay, and column independence. Okay, so let us check what happens with the left inverse and column independence. So when will left inverse exist and when will left inverse not exist? That is something that we will investigate. Okay. So far I have given you examples only of those matrices for which left inverse apparently existed. May not be unique, but at least left inverse existed, right? So can we have examples where left inverse does not exist, for example? So let us see some examples. Okay. So let us try to understand this property first, left inverse and column independence. So if A has left inverse C, then the columns of A are linearly independent. Okay, then the columns of A are linearly independent. Can you prove this? So how do we start proving it? Suppose you want to show the collection of vectors is linearly independent. What do you start with? You start with the linear combination. So AX is equal to 0. That is what we will start with. Okay, so assume that. So prove. How do you prove this? Assume that AX is equal to 0. Then what do we want to show? To prove. What do we want to prove?
X is all zeros.
X is also 0. So if we are able to prove that X is equal to 0, then it means that the columns of A are linearly independent. Is that right? I hope you understand. So columns of A is A1 up to AN, right? So A1, AN, X1 up to Xn. This is actually equal to X1, A1 plus X2, A2 plus Xn, AN. I am saying this is equal to 0. So this is a vector, this is a vector, this is a vector. So you have a linear combination of vectors which is equal to 0. And if that implies that X1 is equal to 0, X2 is equal to 0, Xn is equal to 0. What does that mean? That means that the columns A1, A2, AN are linearly independent. Correct? So that is the meaning of columns being linearly independent, right? So that's what we are doing. We start with a trivial linear combination, Ax is equal to 0, and then we want to prove that X is equal to 0. What is the thing that is given to us? The thing that is given to us, A has left inverse C. That means that C into A is equal to identity. That is what is given to us. C into A is equal to. So start with the 0 vector. So if you start with the 0 vector, then you can write this as C times 0. And then what will you do? C times 0, and this 0 you can write as AX, C times AX, and then you can use the associative property of multiplication, which is CA into X, which is identity into X, which is equal to X. So we have proven that X is equal to 0. That means that the columns of A have to be linearly independent. Do you understand this? You understand the proof? I am using matrix properties. That's all. I am not doing anything else. Is the proof clear?
Yes, sir.
Yes, sir.
So what does that mean? That means that the columns of A are linearly independent. So A has left inverse. So what we have proved? A has left inverse. This implies that columns of A are linearly independent. Can you use this observation to generate examples where the left inverse will not exist?
Where the columns of A are not linearly independent.
Correct. So the places, all the examples where columns of A are not linearly independent, that means that they are linearly dependent. That means that A will not have left inverse. What is the logic that I have used? The logic that I have used here is that this statement is P, this statement is Q, then P implies Q is same as negation Q implies negation P, right? That's the logic I have used. So these two statements are same. P implies Q is same as saying negation Q implies negation P. So that's why Aviraj is saying columns of A, if they are linearly dependent, that means that A will not have left inverse. So what is the most trivial case of columns of A being linearly dependent? What type of matrices? What class of matrices? Wide matrix, correct. All the wide matrices, all the matrices which have more number of columns than rows, they will always have linearly dependent columns. And if the columns are linearly dependent, that means that you cannot have left inverse. So left inverse will not exist for a wide matrix ever, right? So it can exist only for tall matrices or square matrices at best. Do you understand? So I'm going to write, so this observation implies that wide matrices. So what are wide matrices? Matrices with more number of columns than rows. Cannot have left inverse. So now the next question that naturally arises is that can I use this left inverse? How can one use this left inverse? To compute the solution AX is equal to B. Okay, so the first condition, obviously, now that if you want to use left inverse to compute the solution, then the columns of A better be linearly independent, right? So suppose we have linearly independent columns of A, then what will you do? So I will assume that, let us assume that A is left invertible. C is the left inverse of A. Okay, C is a left inverse. Then what happened? How will you use this C to solve AX? So you have AX is equal to B. So what is your guess for the solution? What is your guess for the solution?
X equals to C into B.
C into B is equal to X. That is the guess, right? So how do you do that? So B, so you multiply this CB, right? So what do you get? CB is your guess. So C into B. What is B? B is AX, right? So you can write this as CA into X. What is CA? CA is identity. X is equal to X. Right, so that's the proof. That's the reason why you guess CB, right? So if A is the left inverse, then this will happen. Is this correct? Is this correct? What we have done? Does the left inverse of A exist? Does the left inverse of A exist?
No.
It's got orthogonal columns, so it should.
Correct. It has got orthogonal columns. The columns are orthogonal. We have already seen here in this example. What was the example? If the columns are orthogonal, then what is the left inverse? One candidate of left inverse is A transpose, right? So you just look at A transpose. So A transpose A is actually equal to 1001 identity matrix. So A transpose is a left inverse. Is that right? So what is the solution candidate that you calculated here? CB is equal to X. That's the solution candidate. So what is CB? So CB is basically A transpose B. What is that? A transpose is 100010. That's your left inverse multiplied by 001. What would you get?
0, 0.
So this is equal to X, you are saying. So does AX is equal to B satisfied now for this particular X?
No.
But this is what you told me here.
Sir, B is not in the column space of A.
B is not in the column space of A, correct? That is something that we have to make sure. Existence of left inverse of A is not going to guarantee that. Do you understand this problem? Only having left inverse at our disposal is not enough. We should know for sure that B belongs to the column space of A. That means that the system of linear equations is solvable. So if the system of linear equations is solvable, if this system of linear equations Ax is equal to B is solvable, then you can take a C which is left inverse, and then what the calculation that you have shown will probably make sense. But without the guarantee that the system of equations is solvable, you cannot really say that this is going to happen. So in fact, what you have shown, okay, so first A is left invertible, C X is equal to B has a solution. Okay, so I will add this part here. Okay, this has a solution. Suppose it has a solution, then that solution you can say is given by this. So in this example, by looking at this example, what you have shown really, by looking at this example, what you really have shown is that you find out a left inverse of the matrix and you calculate CB and you check whether that CB is a solution to this system of linear equations or not. If the CB is not the equation, sorry, CB is not the solution, then the system of equations is not solvable actually. So you have devised a mechanism to check if the system of linear equations has solution or not with the help of this left inverse. Okay, so does that make sense to you? So one thing that you should be sure of is that Ax is equal to B has a solution. If Ax is equal to, and something here that we observed tells us that if CB does not satisfy Ax is equal to B, then what happens? Then you cannot have it. So Ax is equal to B is the Ax is equal to B is the X cannot be the solution. CB cannot be the solution to this Ax is equal to B. That means that the system of equations is not solvable. One check that you have done. So left inverse, something interesting we have observed. So let us quickly in one slide summarize it. Okay, so left inverse. Before we close today, let us quickly do this thing. So given A, X is a left inverse if XA is equal to identity. Okay, then wide matrices cannot have left inverse. And why is that? That is true because A is left invertible this implies that columns of A are linearly independent, right? The question that you can ask here is the converse true? That means that if the columns of A are linearly independent, can you say that A is left invertible? So we'll actually prove that that is also true. So these statements are actually equivalent, but so far we have proved only one way implication that if A is left invertible, that means that columns of A are linearly independent. And Ax is equal to B is such that solution exists. Okay, that means that B is in the column space of A. Correct? B is in the column space of A. Then CB, X is equal to CB is a solution where CA is identity. That means that C is the left inverse. And left inverse can be used to determine whether a solution exists or not. So left inverse can be used to determine if a solution to Ax is equal to B exists or not. Okay. So these are the things that we have learned with respect to left inverse. So in tomorrow's class, what we are going to do is we are going to define something which is called as right inverse, which is very similar to what we have done for left inverse, and then combine these two concepts to talk about something which is called as invertibility of the matrix and take the things further from there. Okay, so any doubt about what we have done so far today?
I have a question.
Yeah.
Can you go back to the slide where we proved X equals CB and yeah, this slide. So the next slide.
The next one. Okay.
Yes. So is there a reason why X came out to be all zeros, or is that just coincidence?
I mean, it came out all zeros because I chose A and B in this particular fashion, but it will not be all zeros. Had I chosen B is equal, I mean, if I had chosen B is equal to 1, 1, 1 rather than 0, 0, 1, then also you'll have the same problem that B is not, B is not in the column space of A, but you take B tilde to be equal to 1, 1, 1, and then now you have 1, 1, 1, A transpose multiplied by that, you will get 1, 1. But that also is not a solution. Okay.
Okay.
This is just an example I created. There's nothing big about it. So, and nothing specific like about zero also. It can be anything else.
Okay.
Okay, fine. Ramniva